In this video, we'll take a look at reaction mechanisms and how to determine the rate law for each step and for the overall balanced equation. There are only a few things that you need to remember about these types of problems, and I've listed them off to the side here. First of all, a reaction mechanism consists of elementary steps, and an elementary step is a reaction that takes place in only one step. What's important about that is that the rate law for an elementary step uses the balancing coefficients as reaction orders. Now, this is different than what we've looked at previously when we have a table of data and we have to determine the ratios to figure out m and n, those exponents in the rate law. We don't have to do that when we know that we're looking at an elementary step. We can actually use the balancing coefficients. Now, one of the questions that comes up is, well, how do I know if I can do that? You will always be told either that you're looking at a mechanism, and if so, then you know that the steps are elementary steps, or you'll be told that a reaction is an elementary step. You have to be given that information in order for you to know. If the first step is slow, then the rate law for the overall reaction is equal to the rate law for the slow step. The situation where the first step is fast goes beyond the scope of this class, and we won't be covering that. So the only situation that you'll see here is if the first step is slow. And then finally, the molecularity gives us an indication about how many reactant particles must collide together in order for the reaction to take place. And so the molecularity is equal to the number of reactant particles, and it doesn't matter if those particles are the same or different. You're literally just counting particles. A lot of the work that we do involves strategies that must be taken in a certain order. You must do step 1, then step 2, and so on. And that's not really the case here. So for these problems, we can really answer the questions in any order that we want. The first thing that we'll do here in this example is we will determine the overall or net reaction. And this involves adding up everything that is a reactant and putting it on the reactant side of the arrow, and then everything that is a product, putting it on the product side of the arrow. There are two ways to go about this. The first is you can write down every single substance that appears from all of the elementary steps and then cancel after you've written everything down. The second way is a little bit faster, and you can cancel as you go along. And I'm going to go ahead and show that approach. If we want to cancel something, then it needs to appear on the reactant side in one place and on the product side in another place. Taking a look at the first two reaction steps, we notice that we have N2O4 that appears as a product, and in the next step, N2O4 appears as a reactant, and we can cancel those. Next, we notice that N2O3 does something similar. We have it on the product and reactant side, so we can cancel it. O also appears on the reactant side and the product side. And N2O2 also will cancel. At this point, we'll go ahead and write everything that's left. On the reactant side, we have 2 NO2, and that's all we have on the reactant side. Moving to the product side, we have O2 and 2NO. And it doesn't really matter in which order you write those product substances. Making sure that this is our final net reaction, there's nothing for us to combine, just double checking that it's balanced. And so this is our overall balanced equation. The next thing we'll do is assign the molecularity to each step, and this is as simple as counting the number of reactant particles. So for step number 1, we have 2 molecules of NO2, so that means that the molecularity there is bimolecular. In step 2, we have only 1 molecule of N2O4, so that would be unimolecular. And in reaction 3, we have two reactants, the N2O3 and the O. So that's another bimolecular step. And our final step has only N2O2, and that would be another unimolecular step. Next, we'll write the rate law and determine the reaction order for each step. Remember, as we said earlier, the rate law for an elementary step follows the balancing coefficients. So we simply look at each reaction and extract the rate law directly from that. So reaction number 1, we'll have rate equals K times the concentration of NO2 squared. For reaction 2, rate equals K times concentration of N2O4. Reaction 3, we have rate equals K times N2O3 times oxygen. And for reaction 4, we have rate equals K times N2O2. We obtain the reaction order in the same way that we did way back in the earlier activities, where the overall reaction order for a given rate law is the sum of the exponents. So for reaction 1, this will be second order. Reaction 2, first order. Reaction 3, also second order because we have a 1 plus a 1. And reaction 4, first order. The other thing that I want to point out is the connection between the molecularity and the reaction order. So notice that the two bimolecular steps are second order and the two unimolecular steps are first order. So there's that relationship there, that connection. Next, we want to determine the rate law for the overall reaction. Remember that if the first step is slow, then the overall rate law is the same as the rate law for the slow step. And what we determined just a little bit ago was the rate law for the first step is rate equals K times NO2 squared. So that's the rate law for the overall reaction. To identify any catalysts, we look for a substance that appears first on the reactant side and later on the product side. And that's because a catalyst, while it assists the reaction, it ultimately is not consumed, which means even if it is used a little bit in one of the earlier steps, it must be regenerated in a later step. So we look for something, again, that appears first on the reactant side and later on the product side. And as we look through all of the substances here, we don't see anything. So it turns out that for this particular reaction, there are no catalysts. An intermediate is basically the opposite. It is first produced as a product in an earlier step, and then it goes on to serve as a reactant in a later step. We have quite a few intermediates in this particular reaction mechanism. The first one is N2O4. First appears as a product and then is used as a reactant. N2O3, same idea. First as a product, then as a reactant. Oxygen, product first, then reactant. And N2O2. So there are 4 intermediates in this reaction mechanism. N2O4, N2O3, oxygen, and N2O2.